Welcome to another episode of Between Two Plants. I'm your host, Ian Fife, and today we have a very special guest, Dr. Ola Opara. Welcome, Ola.
Good to be here.
So, Ola, tell me, how did you come to work at WesTech?
So WesTech actually acquired my company back in 2021. We developed this technology, the EBR, and then we were a University of Utah startup. And WesTech acquired us, and I came in with the deal.
Fantastic. And now you are a product manager at WesTech currently, specializing on the technology that you invented, which is the Electro-Biochemical Reactor, correct?
That's correct.
Fantastic. Well, what interested you in water and wastewater to begin with?
Ever since I was a little kid, I wanted to do something that was related to environmental protection or environmental stewardship. And so I did my bachelor within the environmental chemistry field. And when I started my graduate studies, I ventured towards mining and water treatment needs that mine sites have. That's such a unique need that's often forgotten. Once I graduated with my master's degree, I had a chance to either go and work for one of those mining companies or start my PhD. And I was lucky enough to meet Jack Adams, who became my PhD advisor. And he had this really cool idea about this new wave of bioreactors, and he needed help. And that's how I got involved with water treatment.
That's a great story. And I just mentioned, but you are the inventor of the Electro-Biochemical Reactor, or we'll call it the EBR for short, for the rest of our podcast here. Tell me a little bit about how that came about, the EBR system.
Yeah, that's right. So it started as a University of Utah startup. Jack Adams had this really great idea of helping move the bioreactors to the next generation of performance. And he needed some help with commercialization efforts, with organizing the lab, running pilot field studies. And that's where I came in, and we partnered, and we've been great friends ever since.
Fantastic. So let's dive a little bit more into, tell me, what is an electrobiochemical reactor and how is it different than other biochemical reactors?
So conventional bioreactors just use microbes to get rid of contaminants such as nitrate or selenate. And the way that microbes do it is that they use those components just the way that you and I use oxygen. So they use it for respiration, for breathing. And in that process, they require electrons to reduce those contaminants to something like nitrogen gas or elemental selenium. Because they require electrons, conventional bioreactors provide those electrons from organic electron donors. And that's just a very technical term meaning organics. So it can be alcohols, it can be acetate, it can be sugars. People used molasses in the past. The problem is that those organics have to be metabolized first. And metabolism is very finicky, right? It depends on pH, temperature, time of the day, like what moods the microbes were this morning, right? So to compensate for that inefficiency, the conventional bioreactors just overfeed that organic carbon. And now, Ian, what happens if you overfeed a living organism with too much food?
Well, they get fat.
Yeah, that's right. So what happens is that those conventional bioreactors, they work as intended, right? They remove nitrates, they remove selenium, but the unintended consequence is that they produce a lot of biomass because they're being overfed all of this food source. And so then you're creating another problem that you have to deal with. It's the TSS, the biofilm biomass removal on the back end, and it becomes just a very operationally heavy burden. What EBR does differently is that we divorce the supply of electrons from the organic nutrient feed. We say, here, bugs, we're going to give you just enough carbon and nitrogen and phosphorus so that you can grow and do this work we need you to do, but we're not going to give you 10 times as much of nutrients. You're going to get those electrons directly from a 3-volt low amperage power supply. That's how we differ.
You can see why she has a PhD in her title. Maybe tell us a little bit more about what are some of the advantage of an EBR process, especially as we've talked about compared to other biochemical reactors.
One of the biggest advantages is number one, because we're not overfeeding the nutrients, you significantly reduce your operating costs. Those nutrients that chemical organic supply, that can mean 80% of your operating costs for those plants. Now, if we can cut that by 50, 70%, that means hundreds of thousands of dollars, sometimes millions of dollars of savings on the operating costs. That also means that because we're not overfeeding, we're not overdosing that organic carbon, we're not producing all of the biomass. So it means that those reactors are easier to operate and they don't require very complicated post-treatments as other conventional systems do.
That's due to the lack of there's not excess biomass that's being built up, right?
That's right. That's right. There's less biomass, less biosolids that have to be removed in the post-treatment. Provision of electrons directly also means that those EBR reactors are much more efficient, have smaller footprint, and provide just better process control than conventional biosystems.
Tell me a little bit about retention time. I know that in the world of reactors and things, that retention time is a big deal. Maybe talk about that for just a moment.
The main design parameter for bioreactors is called HRT, hydraulic retention time. And it really defines the amount of time that the bugs have to work on your contaminant. We see great improvements in terms of the HRT in the EBR as compared to conventional bioreactor technologies. We just ran a rental system out in southern Utah, where a client has an existing conventional biotreatment that operated somewhere between 5 to 7 hour retention time while not meeting the nitrate treatment targets. We deployed our EBR system on site as a temporary rental solution to help them meet the water requirements throughout the summer season, and demonstrated that our HRT was 30 minutes. So that's a huge difference between 5 to 7 hours to 30 minutes. And really what that HRT defines is the size of your tanks, which means the footprint that your bioplant will have.
So I imagine an EBR is not suited for tackling every water problem out there. So tell me, what is this EBR best suited to treat and handle?
We focus on nitrates and selenium. Those are the two parameters that are our core focus. But I will say that there are also other metals that I refer to as secondary targets. And what I mean by that is if there's nitrate and or selenium in the water, and there's also, say, molybdenum, or there's also antimony, we will pull those metals out of solution as well, because microbes are not really very picky, right? They're going to go after whatever gives them energy. But we will not target only those contaminants, right? Because as you mentioned, the EBR is not a silver bullet. So if there's a water that doesn't have nitrates and or selenium, we would not apply this technology just for arsenic removal. There are much better suited chemical technologies that can remove arsenic much more efficiently than a biosystem.
You heard it here. It's not a silver bullet, so you can't kill a werewolf with the EBR. I'm sorry, folks. So these contaminants, tell me about, nitrate, selenium. What are other methods that can be used to go after those contaminants, and when might an EBR be the better option?
So at WesTech, we offer a very wide portfolio of water treatment technologies. And specifically for nitrate and selenium, the only two other methods that are available out there are reverse osmosis filtration or ion exchange. Both of those work really well at removing selenium and nitrates. The limitation of those two technologies is that they do not transform or destroy those contaminants. They just concentrate them into a brine stream. And so if a client is in a position where they can dispose of that waste product, that waste concentrated brine stream, then those are the technologies that we would recommend they use. If they have a limitation on what they can do with those brines, which we see more and more often now, that's when biological treatments come into play because we're not producing any concentrated waste. We convert nitrate to nitrogen gas and precipitate selenium or selenate and selenite ions as elemental selenium metals.
Ola, I have to ask, when would you use an EBR over other biochemical reactors? Or let me flip that question. When would you use a biochemical reactor over an EBR?
Never.
You heard it here. Ola, tell me a little bit about what use cases are best suited for an EBR.
The two markets that we're currently pursuing are groundwater denitrification and mine water treatment. Within the groundwater denitrification space, we see that more and more of our American groundwaters, drinking waters, are being polluted with nitrates from overfilterization during agricultural activities. Now that we see more and more water scarcity, especially in the West, but also surprisingly in the Midwest and back east, tapping into those contaminated groundwater resources becomes more and more of a priority. And then on the other side, we have mine water treatment, so very complex water chemistries where we see nitrate present from both residual blasting components as well as from cyanide degradation in heap leach operations for gold recovery. And we see selenium just being naturally released from the ore during processing.
I hear that you help run a biological lab. Tell me a little bit about what you do there and why that and how that plays into the EBR technology.
Oh, how much time do we have? So I will say that one of the lessons that we learned with the EBR early on was that many of our competitors treat the bioreactors the same way that you would treat any other mechanical water treatment process, which means that they kind of forget about the guys that are actually doing the work, the microbes themselves. So we took another approach to designing bioreactors. Over the past 20 years, we've been collecting specific microbes, so say denitrifiers that can remove nitrates, selenium reducers, arsenic reducers, and so on and so forth. And so right now we have a repository of microbes, a fridge that's full of microbes that we collected in the environment that just grew naturally to target those contaminants. And what we see is that, we can have 200 nitrate reducers, and you can put all of them separately in a given water chemistry, and some of them will do great, and some of them will not do so great. And then you can flip it and you can put them in a completely different water chemistry, and those guys that weren't doing great in your first case suddenly are really outperforming the other guys. It just means that different microbes have different abilities in different environments, which should not be surprising, right? So the way that we utilize our lab is that we actually pre-select the A team. We create microbial consortia that are well suited to every case, especially with very complex mine water treatment or industrial water treatment, because that bit of an advantage means very fast startup, unlike conventional bioreactors that just, put the equipment on site, load some media in there, and wait for the naturally occurring microbes that may or may not be present in your source water to start growing on the media, right? It means that they have very long startups, and when we start with the inoculum, with the guys that know what they're doing in this water chemistry, we can start up within a week to 2 weeks.
So basically what you're saying is that instead of just hoping that the naturally occurring organisms in the source water will treat these contaminants, you are going and handpicking the best options to make sure we get the best performance and the most efficient performance out of these EBRs.
That's correct. And so that gives us that control to start with, right? It's not an unknown how long we're going to wait and what end performance we're going to reach. Because if you don't know what's in your source water, you may get lucky and they might be there at concentrations high enough that they will establish themselves within a month or two. But you may be not so lucky, and I've seen those cases where it takes 6 months and your performance is very mediocre.
I must say, whenever I start growing microorganisms in my fridge, I usually toss them out. You keep them.
I keep them, and hopefully you toss them out sooner than after a week or so. I keep them. I keep them. I've kept them for 20 years.
Fantastic. Ola, on a more personal side, what do you enjoy most about solving water and water issues?
I do enjoy complex water treatment problems. So systems where we have multiple contaminants and we have to develop a solution to treat this water and think about the order of unit processes uh, that that will give us the water quality that we need at the end.
Fantastic. Where do you think the EBR is being underutilized, or what use cases, where do you think there might have greatest impact for use of the EBR?
Currently, because it is a new technology and we're still going through all the regulatory approvals, I think that the groundwater denitrification market is one that's currently underutilized. Historically, there's been this kind of ick factor with using biology for drinking water, right? People are afraid of microbes. They don't want to use bacteria in front of their water distribution systems. But that's changing now. And I think regulators, engineers, technology providers were all coming to a conclusion that there are no better options than biological treatments for those scenarios. And so I think that in the future, um, the United States market will probably go in the same direction as Europe did years ago, where we start seeing more and more of those biological systems applied in the drinking water market.
As a technology developer, entrepreneur, I imagine that this technology is like a child that's your baby, right? That you've seen grow from the idea to what I understand to be the first full-scale installation going in and starting up here shortly. Tell me a little bit about that journey and how that has felt and how it feels to have a full-scale installation about to start up.
That's it's been a very emotional journey. The PM on the project that Ian just mentioned just told me the other day we have 6 EBR reactors going in on this site, and I have a small child at home, and my PM told me, well, starting in November you'll have 7 children to take care of, and it truly feels like that. It is a an emotional journey to start a company and go through the commercialization of the technology in a space that's really crowded with very big players, right? And being able to bring an idea, a concept from a university stage to something that actually exists in the real world is it's an amazing feeling, and it's very emotional.
Well, congratulations to you. That's very exciting, and we're excited to see what happens with the EBR technology. I'm sure it's always hard to kind of get that first one or two full scale under your belt, and then from there, it just seems like there's often a surge and excitement around it. So, wishing you all the best as we continue to move that product and technology forward. And any other final comments you want to share with us before we wrap up our episode here today?
Thank you, Ian. I appreciate the time being here. I do agree with you that I think one of the biggest commercial challenges of any new technologies is to just get those first few installations in place, being able to demonstrate to our clients, to our engineers, that it works. And I do hope that this means that a new chapter is opening for us and for WesTech moving forward. Thank you.
Well, hopefully we'll have you back on a future episode and you can report on the dozens of installations that are now out there. So we wish you all the best.
Fantastic. Thank you so much.